also can have equality here, which is fine. But J is strictly less than K, and K is less than or equal to M, and this is strictly less than M. So you are talking about the 4 instance vectors. So J is somewhere here, K is somewhere here, M is somewhere here, and N is somewhere here. Okay? And I would like to make you consider about say Zk minus Zj. So what would be these gains? So these gains are going to be the gains from jth gain, okay, equal to jth gain
to the gain.
Jth gain actually, and what would be Zn minus Zm
M to N.
I from M to N. Okay, and we also know about that, and it's very natural to assume that this Li or the sequence of Li is basically IIDs. They are IIDs. So they are independent. In other words, the outcome of one game is not influencing the upcoming game or previous game actually. Okay. They are not influenced by the previous game. So all of these are IIDs. So what you can say immediately? So this sum must be independent of this sum actually. Okay? Because you are talking about so one sum is there, so your gains in this interval must be independent of your gains in this intervals actually. Okay? So the increments in gains are independent. Okay? So these are independent things actually. Okay? So making little observations actually. We also know about the random walk, that this guy is a martingale. Okay? Martingale. With respect to, the natural filtration generated by, the same process actually. Okay? It's filtration generated by. So it's a martingale with respect to the natural filtration. Okay? By the way, what would be the variance of an increment? Zn minus Zm. So what would be the variance of this? So it's going to be variance of Zn minus variance of Zm actually, because
Independent covariance.
they all are independent, but in Zn you also have Zn. So this is going to be the variance of the sum of I equal to 1 to n, d1 to n, m to n, Li's actually. Okay, so this is the variance. Now all these are independent, so the variance of the sum is the sum of the variances actually. And what is the variance of each Li?
1.
So it must be 1 actually. Okay, it must be 1. So if the variance of each Li is 1, this must be what?
N minus M.
So it must be n minus m actually. Okay, so the variance of. Okay, so the variance of your gains is basically precisely equal to, the difference of the times between n and m. Okay. So this is about the random walk. So what I would like to do now, so if you want to see random walk pictorially, how does it going to look like, are the gains pictorially? So, you're going to have, so you will start from here, and it can go here, and then it can go maybe even further, and that can go down, and then up, and go down, down, down. Okay, so that is, so these are the gains actually. Okay, so it's n versus Zn graph actually. So initially your graph is 1, so that's one trajectory that random walk can have. Then you gain $1, you go again another $, $n, and then you lost $1. Okay, lost lost dollar, gain dollar, and so on and so forth actually. So cumulative gains actually. So what I would like to do now, I would like to, the next thing that I would like to do, that I would like to quickly join these points by, you know, what do you say, linear lines actually. Okay? So when I'm going to join these lines, so how does this is going to look like the picture? You know, the every trajectory is going to look like something like this actually. Okay? And then, and for example, we may assume that each of this is happening on an interval. So for example, at the moment, each of this is happening at, for example, 1 instant actually. Okay? So, but when I'm linearizing it, so the good thing about that is going to be, you can also talk about the gains within that instance actually. Are you getting the point? You are making it a continuous trajectory. Okay? Then I would like to do what? That if I shrink these intervals sufficiently. So imagine that I'm not, you know, playing a game after every minute, but I'm playing a game after every second actually. Or maybe, you know, if I keep on decreasing the time, I'm playing the same game after, say, every nanosecond or microsecond or something like that. So this jiggling will go continuously. So I would like to, so in other words, I would like to create this process and then I would like to consider the limit of it. Okay? And then I would like to ask a question that once you have such a limiting process or the limit of such a process, does it going to still inherit these properties? Are these properties are going to be still there actually? Are some of the properties are going to miss? The answer is that these properties are going to be still there. So let's see how. Okay? So we did it already. I'm not going to spend a lot of time on it, but I was just going to spend some time with this notation actually, and then, you know, I would like to move towards, you know, Brownian motion actually. The key definition of the Brownian motion. Okay. And the definition of Brownian motion is going to be something similar. So there's going to be, it's a process, okay, that has such and such properties, whose increments are independent, which is also a martingale and, you know, similar kind of properties. So I'll define it precisely. So I would like to do next what? I would like to scale the random walk now. So instead of playing the game after every minute, I would like to, you know, play the same game, you know, really quickly. Okay? One second.
सर उन्हनि खे एक्सटेंशन वठी ॾिनी पोइ शीशे वारो दरवाज़ो चई पोर्शन खे आहे न गैलरी टाइप खे उते विहारे छॾियो ताकी आवाज़ घटि में घटि अचे
ठीक है जी. So let's move ahead. So what should I do? Andy, what should I do? How should I, you know, I would like to bring this Zn into roughly continuous time framework. It's like passing the limit. Doing the same thing, but doing it frequently. So how can I start? Let's assume. So how can I do it? So what would be? So how can I talk about the within instance actually? So what would be the recipe to talk about, for example, within instance? So you have discrete instance 1, 2, and 3, and 4. So how can I talk about within them actually? Okay.
linear algebra.
Okay, so I'm talking about the instants actually. So I have instance 1, 2, 3. So I would like to talk about some time that is, that is in between these two instants, for example. So what we can do, so the idea is this. So take two instants, okay, and split them into, for example, n parts. Okay. Well, each of this subinterval has a length h. And then what you're going to do, take h goes to 0. Okay, so h should depend on, the number of, the subintervals that I'm making within an instant actually. Okay. So the idea is this, that now let us introduce the notation, say t, okay, and the t is basically the multiple of an h, okay, where h is what? So let's assume, for the sake of simplicity, let's take h to be, say, capital 1 over n. Okay, so in other words, each instant 1 to 2 is being divided into n parts. Okay, so each instant, so n to n plus 1 is being divided into n equally parts, okay, where each of them has length h, okay, and the t equal to nh could be any of these, what we call points. Okay. So you know how to discretize things. You know how to. And let me define, okay, what will be the meaning of L. So previously we defined that my gain at the instant n, but now I must be able to talk about my gains after, say, some really small instant h actually, okay, or at instant, for example, k, okay, but the division between the instant has been, for example, done by half. Let's write it in this manner, that I'm denoting it LH. So h is just for the reminder that you have divided the entire timeline into the subintervals of length h actually, okay, and I'm evaluating it at, for example, time k. So what should be the meaning of it? The meaning of it, I'm defining it to be the square root of h times Lk. Okay. Square root of h times Lk. So Lk is what? It's this actually. So your outcome of the nth game actually. Okay. And I'm multiplying with a small quantity, square root of h actually. Okay. So that's what is my definition. So what would be this precisely? So I know that Lk could be 1 or minus 1. So in other words, your gains can go up and down instead of 1 and minus 1. They can go with, say, for example, plus minus a square root of h actually. Okay, where h is a small quantity. So either in other words, that either you are losing something really small or you are gaining something really small actually. Okay, square root of h. So why I'm choosing it, there is a reason. So that all those properties that I was interested should preserve actually. Okay, there are other ways as well, but this is the pretty random form. So in other words, what this was happening, for example, for your gains. So your gain went from, for example, this $1 to $2 between the instant 1 to 2. So now you are bringing this, so you are kind of scaling it actually, okay, you are scaling it, so you are bringing this, this gain really closer to basically, your previous gains at that time actually.
Sir, what's the k?
I'm sorry? So the k is,
It seems
so
the
the k
natural
is the discrete instance.
if k is a natural number, sir, what about those that are not natural numbers?
I'm sorry.
Like we can now talk about small intervals and the numbers that are between natural numbers. But what about those? You are not talking about those.
What numbers that?
That are not real. That are not natural. Yes.
No, I mean, okay. So what we are saying is that, think about it. So what we are saying is this. So we said you have two instants, okay? Say, k minus 1, k and k plus 1. Okay, so you have two instants. This is a way to define the gains between two instants actually. But between two instants at what time? So after every h, a small h actually, where h is what? It's like splitting this entire interval into the n parts and then talking about the gains at each of these such subsets actually. Okay? So I know that from k to k plus 1, either I can go a step up, $1 up or $1 down actually. But now instead of going $1 up and $1 down, I'm saying that on each of such steps I'm going either up by square root of h, a small amount is square root of h or square root of minus the square root of h actually. I'll move ahead and everything will make sense actually. Don't worry about it. So now I would like to define, what do you say this? Scale the random walk. Okay? So, I mean, if you want to visualize it, what I'm doing, so you have this macro random walk, okay, happening at, discrete instance. I want to scale it down. So think about it. Okay, so I want to scale it down. So think about fractal actually in your head. Okay, so how does a fractal look like? That, no matter how deep you go into the fractal, it looks like the same actually. So what I'm going to do, I would like to create roughly a fractal behavior of it, that if you see the random walk, macroscopically or microscopically, it would look like the same. And it has all these properties that I talked about it. So scaling it down to the small level. So therefore I'm defining ZH at any time t. Okay? ZH at any time t, my gains at any time t, where t can be, any instant nh is what? So L over n. So, if it is, for example, if h is, if we are splitting into, for example, an interval into 10 parts, then nh means what? So if n is 1, so you are talking about 110 and 210 and 310 and so on and so forth. Okay? So that h of t, in other words, a scale random walk, I'm defining it to be the sum of such kind of gains actually, some tiny gains. So this is going to be k equal to 1 to n, and h of k, where the t is an h. Okay? And this is also, so on these instants, it's this sum, while on the instants which are other than these discrete instants actually. Okay? In other words, and this expression is some linear expression for sum for t in the interval, say n k to n plus 1 h actually. Okay? So I have this interval, for example 0 to 1. I broke it down into many parts. Okay? Previously I have only one value defined at this part 1, that it could be $1 or it could be less than $1. Now I have my gains can go up and down, okay, with a small magnitude on all of these small points. And now I'm doing what? Within these points actually. Okay, so if I want to define, for example, the gains not only at these small discrete points but also within these points actually. So what I need to do, so I'm going to interpolate actually. Okay, so I'm interpolating the values. So in other words, I am connecting them with small lines. That's what I'm connecting them with small lines. So in this manner, this gain process is not only defined at all these instants, but it's also defined on within these intervals as well actually. Okay, and by linear, what do I mean? We mean what? Okay, so I mean, if you think geometrically, so you have 2 points in the plane with some coordinates. So how you can find the equation of a line that connects that point? Okay. So you can apply your geometry formula, the 2-point formula, the interpolation formula. So you can put that expression here. Okay, so that's what I'm saying. So now, the good thing that happens about this process is that this ZH process of the scale random walk has become a continuous process. जी आप कुछ कह रहे थे?
सर ये जो h और k आपने मतलब डिफाइन किया, h और k के दरमियान क्या रिलेशन है?
क्या मतलब? So
k और h दोनों को देखें तो
k और h के दरमियान ये रिलेशनशिप है, ठीक है? So k is the discrete instant. So k is the discrete instant. So k is a number for 10 and 11. Okay? And I'm saying that within 10 and 11 I have broken down it into the n parts. Okay? With each interval h. So this instant is going to be what? So this is 10, so this is going to be 10 plus h. Okay? 10 plus h and 10 plus 2h and so on and so forth. Okay? और हम ये कह रहे हैं कि from k to when you are going to k plus h or 10 to 10 plus h, your gains either can go up by square root of h or can go up by square root of minus h. ठीक है? That's what it is. We talked about it. Okay. Can I have a clear expression for ZH, say evaluated, say at a time t, and that time t, for example, is NH? What do you think? What should be this expression? Okay. Maybe an exercise to verify is going to be that this is going to be the square root of h is at n actually. Okay, the square root of h is at n. Okay. Can you see why it should be square root of h is at n?
Because we are splitting k interval into n parts, we are multiplying n with h. So it will become, I think so, k.
So it's something like this actually. So the way you if you keep this in your head actually, and then you substitute values here, you will see that it's going to be square root of h is at n because what are the LHKs actually? The LHKs are square root of h LKs. Okay, substitute it and what are you gonna get? So substitute this value here, pull the square root of h out, and sum of LKs is going to be Zn. Okay, from 1 to n. Okay. You can see that. In other words, the scale the random walk evaluated at a time nh, and nh is what? nh is not. So it's one of the discrete instant actually. So we are talking about the discrete instant. So if you want to talk, so I know that if I'm talking about a discrete instant, that h is going to be this expression. You take this, substitute it here, pull the square root of h out, and take the sum, so it's going to be square root of h. Okay? All right. Now let's see what property does it have. So if I evaluate ZH at 0, what are you going to get? What are you going to get?
0 y.
0. Because Zn is if I take, for example, 4 instance, say R, S, and T, and U, and I'm talking about, say, ZS minus ZR, and I talk about, say, ZU minus ZT. So what you can say about, you know,
ZH or just Z?
Sorry?
Z sub H or just Z?
Obviously ZH.
Obviously.
Yes.
It's just the same radical list.
Same thing. So we know that these are independent, so these must be independent too. If you compute expectation of ZH, which is going to be, you know, H times square root of Zn, so 0. Variance of ZHn is going to be the variance of square root of H Zn, but you know I can pull this out of variance, it will become H actually because you need to square it, and the variance of Zn is, you know, n simply. It's simply n. Okay. So you can keep it. So what is Zn? Zn is a sum from 0 to say n game actually of Li. So take the variance. H, alright, and you can also see that this scale version is martingale as well. So there's all other properties that, you know, random walk has. This scaled random walk also has it. You can also verify some of its more properties. You know, there's variation and quadratic variation and all that. So read it out from here. So I'm not getting into all that. You can also prove this. I know that Z square n minus n is a martingale. You remember? So we can prove that Z square minus n is a martingale. And similarly, you can show here that ZH of
NH.
say NH minus NH is a martingale as well. So it's a martingale. So you can read it from the book. I'll keep this on reading this. You can see the basic properties of scale random variable, that all those properties which were there in random walk, if you scale that random walk to microscopic level, the properties are still there actually. Okay? Last thing. And then I will throw the definition of Brownian motion. Now, consider the scaled random walk, okay, the same random walk, but for example, take time t equal to 1. So what what would be ZH evaluated at 1? What it would be? So you have an expression for ZH of NH.